Good morning, sir. My name is Vaishnavi. I am from CSE C section. Today, my topic is about bidirectional RNNS. Topic is bidirectional RNNS. It is introduction to bidirectional RNNS. Bidirectional RNNS are a type of recurrent neural network designed to process sequential data in both forward and backward directions. They are particularly useful for tasks where context from both past and future input improves performance. This presentation will explore the architecture, advantages, and applications of bidirectional RNNS. It is a recurrent neural network. Basic recurrent neural networks are neural networks that process sequential data by maintaining a hidden state. They update their hidden state based on the current input and previous hidden state. RNNs are commonly used for language modeling, speech recognition, and time series analysis. And here we can observe the picture outputs, which is forward layer, backward layer, and the user given by the inputs, and we can observe the outputs from back forward layer and also backward layer. Moving forward for the limitations of standard RNNS. Traditional RNNs process data unidirectionally, either forward or backward, which limits context understanding. They often suffer from vanishing or exploiting gradient problems during training. These limitations can reduce the effectiveness of RNNs in capturing long-range dependencies. And here we can observe the bidirectional RNNs forward and also backward. Concept of bidirectional RNNs. Bidirectional RNNs extend standard RNNs by incorporating two separate hidden layers, one processing forward and another also backward. The outputs from both directions are combined to produce a context-aware output. This architecture allows the network to utilize information from both past and future inputs simultaneously. Architecture of bidirectional RNNs. The architecture consists of two RNS layers, which is one that process input sequences from start to end, and another one is end to start. It happens in two types, which is start to end and also end to start. The outputs of these layers are consecuted or combined to form the final output at each step. We can observe the result in each step. This setup enables the model to have complete context for every position in the sequence. Types of bidirectional RNNs. Bidirectional simple RNNs use basic recurrent units for processing sequences. Bidirectional STM, long short-term memory, new networks mitigate vanishing gradient issues. Bidirectional GRUs, gated recurrent units, offer a simpler alternative with comparable performance to LSTM. Here we can observe unidirectional RNN and also bidirectional RNN. We can observe input and also output past to present. Outputs will be conjugated. Bidirectional STM, BILSTMs incorporate memory cells that can log long-term dependencies in sequences. They process data in both directions, capturing context from past and future inputs. BILSTMs are widely used in NLP, natural language processing tasks, such as machine translation and named entity recognition. Bidirectional GRU are similar to BLSTMs but have fewer parameters, making them faster to train. They use gating mechanisms to control information flow and handle vanishing gradients. BIGRUs are effective for real-time applications due to their efficiency. Here we can observe the advantages of bidirectional RNN. They provide richer context by analyzing sequences in both directions. They improve performance in tasks requiring understanding of entire sequences. They are capable of capturing long range dependencies more effectively than unidirectional RNN. Here we can observe bidirectional RNN for sequence classification. Challenges in bidirectional RNN: they require access to entire sequence before processing, limiting real-time applications, increased conceptual complexity and memory usage compared to unidirectional RNNs, proper handling of variable length increases, needs additional techniques like padding and masking. Here we can observe the backward pass and forward pass concatenation. Here we can observe first the tokens, the cat, sat, and down. At the end, we are going to observe the concatenation. Applications in natural language processing. Bidirectional RNNs are used in natural language processing. How they are used? Here we can observe. Used for text classification tasks like sentiment analysis. They enhance machine translation systems by understanding context from both directions. Named entity recognition (NER) benefits from bidirectional context to identify entities accurately. Here we can observe architecture, combined output, and also forward and backward direction, which is happens at applications in speech recognition. They help improve phenomenon and forward recognition by considering surrounding audio frames. Bidirectional RNNs enable more accurate transcription of speech signals. They are used in voice assistants and also automated transcription services. Applications in bioinformatics. Bidirectional also used in analyzing of DNA and protein sequences to identify functional regions. They assist in predicting secondary structures in biological sequences. Their ability to capture long distance dependencies is available in genomics research. Training bidirectional RNNs. Training involves backpropagation through BPTT to update network weights. Techniques like dropout and gradient clipping help prevent overfitting and stabilizing training. Processing sequences and proper batching are essential for efficient training. Evaluation metrics. Performance of bidirectional is evaluated using accuracy, precision, and also recall. Sequence labeling tasks often utilize F1 score for balanced performance. Cross-validation ensures the model generalizes well to unseen data. Recent advances and variants. Attention mechanisms integrated with bidirectional RNNs to enhance focus on relevant sequence paths. Hybrid models combining CNNs and RNNs leverage local features and sequential dependencies. Recent research explores transformer architectures are alternative, but bidirectional RNNs remain relevant. Future trend in bidirectional RNS. Integration with transformers and self-attention modules is an ongoing research area. Development of more efficient architectures for real-time applications continues. Expanding applications in multimodal data processing is a promising direction. This is the future trends which gonna happen in future by the bidirectional RNNs. Practical considerations: we can observe choosing between LSTM, GRU, or simple RNNs depends on task complexity, available resources. Proper processing and sequence management are critical for optimal performance. Model interpretability remains a challenge, but visualization tools can aid understanding. Conclusion: by this bidirectional RNNs, we can conclude significantly enhance sequential data by modeling leveraging full context. Their versatility and strong performance to continue drive research and application development. Understanding their architecture and limitations is essential for deploying effective sequence based models. And thank you.